Okay, welcome. Welcome to the inaugural lecture of Professor Michele Coti Zelati, both to the in-person and to the online audience. This event will be live streamed and recorded. My name is Axel Gandhi. I'm the head of the Department of Mathematics. Now, in the event of a fire alarm, please follow the emergency exit signs to leave the lecture theater, and the assembly point is Dangur Plaza, opposite the main entrance to the Sir Alexander Fleming building. After the talk, we'll have a Q&A session. Virtual attendees are invited to ask questions via the live stream chat. Now, let me introduce Professor Coti Zelati. He's a mathematician specializing in analysis, probability, and dynamical systems. Born in a small town on Lake Como, he earned his PhD from Indiana University in 2014 before moving to the University of Maryland as a Brin postdoctoral fellow. Since 2017, he has been at Imperial. His research focuses on fluid mechanics and kinetic theory, particularly hydrodynamic stability, mixing, and turbulence. He was awarded a Royal Society University Research Fellowship in 2019 and an ERC starting grant in 2022. It's great to have him in the department, and in principle, I'm very much looking forward to his inaugural lecture. However, I was a bit perplexed when reading the title of his lecture. I always thought that mathematicians are machines that turn coffee into theorems. This is, of course, why we recently installed new coffee machines in our common room. The use of these machines is so heavy that they constantly need servicing and refilling. So I was already looking forward to an uptick in the number of theorems coming out of our department. I very much hope that Michele will not be telling me that I should have just bought a couple of tea bags instead. The audience, I give you Professor Coti Zelati.
All right. Thank you so much, Axel, for the nice introduction, and thank you all for being here. It's kind of amazing that there are so many people in this room today with the weather that's outside. I'm really excited to give this lecture. It's my first public lecture that I've ever given, and I thought, the title should be sort of representative of what I do as a researcher. As an Italian, I will switch to coffee very, very quickly. So tea is just because of English language. So when I started thinking about this lecture, I thought of when I applied for the Royal Society Fellowship back in 2018, and I had to write a layman summary. And so what I started thinking about is, okay, what are nice fluid pictures? And there is a great book that's called the Album of Fluid Motion, in which you can find a bunch of pictures like this. And in particular, this one, I thought it was very easy to explain to anyone. So this is 3 snapshots of a fluid past an obstacle. So you can think of looking at a river from above, and that's like a section of the pillar of a bridge. And what varies in these 3 pictures are the flow rates. So here, you can think of the river moving very, very slowly. And the sort of fluid motion that you see is kind of a well-ordered picture. And as soon as you increase the flow rates, right, you see that maybe some more complicated structures appear. And so when I was writing the layman summary, I had to write, I don't know, like 3 paragraphs. And I filled it with a bunch of keywords that you see written here. So stability, dissipation, mixing, coherence structure, laminar versus turbulent flows, small and large scale, zero reversibility. And what I did, I read it to my mom, and who was a French teacher. So no math background for her. And so I kind of read all these 3 paragraphs by putting a lot of quotes when I was saying a sort of a keyword, thinking that this would make it more understandable, right? If you just put quotation marks around technical words. And so what she told me was something on the line, look, Michele, I love you, but I didn't understand anything you just said. And so what I tried to take this constructive criticism and put it in an actual layman's summary, which started with the same sentence I started the abstract of this lecture. So it started with what do hurricanes, magnetic fields, and cups of tea have in common? So, and the keyword, the only keyword that I wanted to focus on was mixing, which is a word that it's commonly used by everyone. So, of course, I'm hoping that everyone has experienced at least 2 or the 3 things that are pictured here. So one is mixing milk and coffee or tea together. And one is the magnetic field of the Earth, which, whether you're aware or not, you're experiencing every day. Hopefully, not many of you have experienced a hurricane in your life. But it turns out that essentially the fundamental mechanisms that make this process somehow look similar is what we call mixing, or in particular fluid mixing, as my research. So there is no sound mixing, unfortunately, for my friend Julian, who's a sound engineer, but there is mixing in this sense. OK, so just to give you an idea that the fact that mixing appears in many domains of math. So let me just, well, first of all, it appears in nature before in math. So you can think of many industrial processes which involve mixing. So if you have to mix 2 liquids together. There are also many interesting things in the, say, atmosphere of planets. So here is a picture of course, this doesn't work. So the picture of the red spot of Jupiter. So this is some structure that has been observed for over 200 years. And mathematically, however, we have a vague idea of why it's there, and it evolves maybe very slowly, but it's kind of stable in the atmosphere. And I'll try to maybe link also this picture to what I'm going to say in a while. And a mixer that we know is pretty efficient is the ocean. So here is a video of currents in the oceans that mix various things. You can think of mixing the temperature. So the temperature is transported around the ocean quite efficiently. And also other things like salinity or other quantities that you can find, or pollution for that matters. And, but of course, mixing is also quite relevant in many domains of math. And I list some here. These are maybe keywords that some of you don't really know what they mean, but you know, they're easily Googleable. And for those of you who know me on the workplace, you know that I hate this division between pure and applied math. But still, you know, I put it here a little bit. So what I do, as Axel said at the beginning, is something at the intersection between pure and applied. And the pure, say, subjects that I touch upon are, for example, dynamical system. Mixing flows are a class of flows that are studied quite a bit in this branch of math. Stochastic analysis, when you talk about, say, invariant measures of certain systems through probability theory. And analysis, if you study certain functions between weird spaces, if you like. From the point of view of applied math, there are many applications of mixing. So one of them that I really like is related to math biology is about chemotaxis. So chemotaxis is a process in which certain organisms, like bacteria, for example, they aggregate near a source, say, of food or a reactant. And mixing can prevent this sort of aggregation. We know from some recent or fairly recent work of Mouhot and Villani that the mixing is responsible for the decay of the electric field in a plasma. So that's the second bullet point there, kinetic theory. And of course, the one subject that is closer to my research, if you want, is coming from fluid dynamics, atmospheric science, oceanic science, and is somehow related to turbulence, okay? Which is something that again, we have experience maybe on a plane or something, but mathematically we don't really have a good way of defining it, for example. But to understand turbulence, you have to understand mixing, okay? So what I'm going to try to do today is answer some questions about mixing through the language of math. And you should really think of math as a language that can be translated into English and vice versa, okay? And so that's what I'm going to try to do today. So what are questions that you may want to ask about mixing? So one of them is, for instance, what is the most efficient way to mix two liquids? So I'll give you two liquids together. Can you tell me what's the best steering way that I can use to mix them? Okay? And I can give you 3 examples. So again, the situation you have to think about is in the morning, you're making your breakfast. You want to mix milk and coffee together. And the first way that you can do that is just by pouring the milk into the coffee and wait. Okay? That will do something. You may say it's not the most efficient way. And I may agree. Another way is you steer your mug in a perfect circular way. So you put your blob of milk, and you start steering in somehow a perfect circular way, which you cannot do actually in reality. But think that in an idealized world, you could do it. That's one way to mix milk and coffee. And the third one is you sort of mix at random. So this is not exactly the picture of your mug, of course. But you know, what I'm saying is that you sort of move your spoon in random ways, just maybe as you know, a little kid would just do it, you know, if you ask them. And so I could ask you now, what way would you choose, right, if you have to catch a bus and you're kind of late, right? And I will try to prove to you mathematically which is the way you should choose. And I'm guessing most of you will choose the steering at random. And I can spoil that that's the correct answer. But you know, I want to just tell you exactly why it is. Okay? Okay. So another question that you can think of that is relevant maybe in the real world is how observable is mixing? And one of the keywords that they put at the beginning was stability. So how stable is a process in nature in general? You can think of it as, well, if you can see it, it's probably somewhat stable, this process. Okay, so observable and stable, I will use them interchangeably for this talk. And so what does it mean that you can observe something? It means that if you disturb it a little bit, some way, still the process will look very similar. Okay? So but of course, this depends on the size of disturbance that you're going to put in. Okay? So, and I'll show you an example in a second. But that's sort of a question that you can ask. How big of a disturbance can I allow to still be able to see a certain stable process? Okay? So here is the example. Say that you bring your 5-year-old cousin to the lake. The lake is there, flat. It's a pretty stable thing if you think about, right? It's very observable. And first thing the kid does, it just throws a rock into the river. So it creates some wiggles, right? And then these wiggles, however, these little waves, they will disappear at some point, right? So this is an example of a disturbance that is, you know, small enough so that the stability of this process is not, you know, completely destroyed. But of course, you can think of, you know, throwing something much, much bigger, like an asteroid, in the lake. And this will drive the lake away forever, right? The lake won't be there anymore. But of course, it doesn't mean that the lake at rest is not a stable, observable process, right? It just means that you just disturb it too much. And so it's interesting to see how big of a disturbance, where is the threshold of disturbance, right? You don't want to disturb a process too much. but maybe you want to know how big of a disturbance you can allow. OK, so what in the end I want to show you is how do you prove a theorem about mixing, and how do you prove a theorem about the size of disturbances. But maybe before doing that, when I was writing the slides, I thought, OK, maybe we should take a step back and ask ourselves, what is a theorem? OK? And again, I will do this by examples that hopefully everybody can understand. But in general, a theorem, you can think of it as just a statement. It has some assumptions, some conclusions. OK? And the way you prove it is you use some logical reasoning that start from the assumptions. You deduce something from the assumptions to reach the conclusion. And the conclusion, the statement of the theorem, should be something that is true in every possible situation that is, let's say, compatible with the assumptions. OK? So let me just give you an example of a simple theorem that, in fact, I asked my partner to prove. And she's not a mathematician, but she proved it exactly in the way that is written here. And again, I want to tell you about, well, she proved it in English, right? If we think of math as a different language, she proved it in English. I want to translate it in math language, just because if you just give a proof only in English, people will complain that there is not enough math in it. So, but this is a literal translation, OK? So the theorem is the following. If the sum of two integers is odd, then exactly one of them is even. OK, just think about it. We all know that, OK? And well, the way she proved it was to reason by cases, right? So if both numbers are even, then the sum is even. Okay? Math helps you sort of nail down all the possible details about this. So you have to think of, so the assumptions are that the two integers, the sum of the two integers are odd. And now we're thinking about the case when the two integers are even, right? And so what does it mean to be an even integer? It means that you're divisible by 2. So it means that you can write the integer as twice some other integer. Okay? So capital N is my first integer. I write it as 2 little n. Capital M is the other integer. I write it as 2 little m. And I add them together. So when I add them together, right, I write 2n plus 2m, and then I factor out the 2. And so I wrote the sum, m plus m, as twice another number. So that's an even number. Right? That's the definition of even number. And you see the logical reasoning is through these basic algebraic operations that you do here, right? So you're using, in this case, associativity of adding two numbers. OK? That's what I'm using here. Then the other case, if the two numbers were odd, right, then the sum also, you add two odd numbers, you get an even number. OK, that's how do you write it in math language? Well, an odd number is an even number minus 1. So it's a 2n minus 1 and 2m minus 1. You add them together. You again use some properties of summing integers, right, commutativity and associativity. And then you end up writing the sum, capital M plus capital M, as twice some other number. So you also prove that m plus m is an even number. Okay? And so then it must be that one of them is even and one of them is odd. Okay? That's so this is a complete proof of a theorem. You see that math makes you really think about what each word in English means. Okay? But it's just a simple translation. Some of you may be fluent in math, and some of you may be fluent in English, or in both of them, or in neither of them. Then it's going to be a problem for this lecture, probably. But you see, like, you know, that's just a literal translation from one language to the other. And so now what I want to try to tell you is, OK, how do I prove a theorem about mixing? OK, so mixing, as I said, should model something about reality. So I have to tell you a little bit how do we even start about stating a theorem about mixing. OK, so let's say that we want to describe reality. So let's say, again, the coffee and milk example is just so great that I cannot do without. So, but OK, we live in a three-dimensional space. So I have three space variables, x, y, and z, points in space, and time, right? T. And so I drop the milk in the coffee, and I look at each point in my mug, x, y, z, and I put 1 if there is milk in that point, and 0 if there is coffee in that point. Okay? This is my initial measurement. So for each point x, y, z, I label the point 1 if there is milk, and 0 if there is coffee. Okay? So this gives me a function. From every point in the mug, I assign either 1 or 0. Okay? So this is my initial measurement. I call it f0. And then I need the steering way. I told you that you could steer in a random way. You could steer in a perfect circle. So the steering way is typically modeled as a velocity vector. So u depends on the point in space where you're looking and on the instant in time where you're looking. And it's just the fluid velocity. So if I steer in a certain way, I cause a certain velocity in the fluid, which is described by a vector, right? Intensity and direction. Okay? So that's my steering way. And the unknown, so that I want to find, is the concentration of milk relative to coffee at any later time. So I call this f of t, x, y, z. So you give me a point in space, an instant in time, and I want to tell you 1 or 0, right? Whether there is coffee or milk at that point, at that time. OK? So what is the equation that f solves, right? This becomes a bit harder to explain to anyone, but I'll just start with the simplest equation that you can think of. It's called the transport equation. So it's a partial differential equation, it's called. It's just, think of it as just an equation that f solves. So if you can solve for f, great, you solve the equation. But this equation, you can think also of this as some language, the math language, that some of you may not be fluent in. But the literal translation of this equation is move with the fluid. Okay? This is saying essentially that you steer your fluid in a certain way, and each particle follows the velocity of the fluid that you are imposing. Okay? That's all it says. It doesn't matter whether you know exactly what these symbols are. If you make me read something in Chinese, I won't know any symbol anyway. But if you tell me the translation and I trust you, then I believe that the translation. So this is called the partial differential equation. It's one of the objects I study quite a bit in my research. And it's supposed to describe certain key aspects of the real world. Okay? It's a model. And you can just tell me, well, you have an equation, right? To just solve it, find the solution. And then you know your concentration of milk relative to coffee at any time. So these equations cannot typically be solved explicitly. Okay, so given an initial measurement, given a steering way, I cannot just come up with a formula that tells me, oh, what is f, t, x, y, z is, right? And you give me x, y, z, and t, and I give you 1 or 0. I cannot really write a solution like that. But that's actually a good thing. Okay? So suppose that this equation describes the evolution of temperature in the atmosphere in the world. Okay? And suppose that now you go to the Met Office, right? And you ask, what is the measurement of temperature in the world everywhere now? And then I give you a formula to understand what is the temperature tomorrow and the day after tomorrow, right? At any time. That would make our life very, very boring, right? What are we going to talk about in this country if we know the equations of the weather, right? It's definitely something we cannot expect. And it also gives me a job, so that's this thing. But what you can do is you can still deduce properties of solutions of this equation, okay? Even if you don't know what the solution actually is, okay? So let me just try to tell you a theorem about mixing. And remember, a theorem should have assumptions and conclusions. And I'll try to explain in English what is the math written there. So the first assumption of my theorem about mixing is that the initial volume of milk and coffee is the same. So and this is basically how I would write it in a paper. So I would write that the volume of the set of the points xyz in which f naught, the initial measurement, is 1, this corresponded to milk, is the same as the volume where you have 0. Okay? That's saying same quantity of coffee and milk. And the second thing that I cannot write maybe in precise mathematical words says that the steering way should be sufficiently rich. So what does this mean? So first of all, you have to steer. If you just don't steer, nothing happens. Okay? So u cannot be just a 0 vector. Okay? It has to be rich. But of course, you can think of a situation of this type. So say that you have your mug, you drop milk here, and then you just rigidly rotate, like a planet, this blob of milk. Okay? This doesn't mix anything, right? Because you're not stretching or compressing the blob of milk, right? And so this doesn't do anything. So I want to avoid this sort of trivial cases, trivial in the sense that I'm not doing anything very smart with my milk, if you like. And the conclusion of the theorem is that if you assume these two bullet points, then the steering way you picked mixes all such initial measurements. So whatever the initial measurement is, however you distributed your milk and coffee, right? Your steering way will mix everything. And why do I write it like this? So this is the concentration of milk relative to coffee at later times. And what I'm saying is that eventually it will reach 1/2. So in this slide, 1/2 means caffè latte in English, okay? And why 1/2 is because you have 50% of ones and 50% of 0. The average of it is 1/2, right? And that's what it means. So eventually, you reach a state that is sort of homogenized, and you averaged out your initial measurement. So ones and zeros become 1/2. Of course, you can think of generalizing this in many ways. So this is an example of a theorem that is a bit qualitative, though. So all I'm saying is that whatever the steering way, as long as it's not a trivial one, will be useful for you to mix. But it doesn't answer the question that I asked you in slide 3 or 4, which steering way would you pick? Right? I'm not saying anything about that with this theorem. And so here is a more precise statement about that. So if I steer in a perfect vortex in a perfectly circular way, I can tell you that how fast f reaches 1/2, the end state. And this is somewhat inversely proportional to time, to some power, p. And if you give me the fine properties of your steering way, then I can tell you what p exactly is, okay? P depends on the fine properties of your vortex that you're creating. While if you're steering in a sufficiently random way, okay, so the third example that I showed you in that slide, then f goes exponentially fast to the mixed state, the mixed end state. Okay, so this theorem tells you, okay, that you should pick the random mixing or random velocity field, right? The random mixing, to hope to catch your bus, essentially, right, in the morning. And these are theorems that I proved over the years with a few collaborators, Jacob Bedrosian, Michele Dolce, and many others. And to some extent, I still think about these sort of problems. So this is an example of a quantitative theorem, right? I'm not telling you that f goes to 1/2. I'm telling you how fast it goes. You have to remember, of course, that exponentials are much faster than polynomials, right? So that's how you conclude that the random steering way is faster than the vortex way. OK, so now you can ask, OK, but what about the real world, in the sense that, OK, this is you're coming up with a model. It's this simple model that just says move with the flow, right? Move with the fluid. But what if you want to take into account more effects, OK? It's not about steering in the end of the world, or the ocean dynamics, right? It's not about how particles only move. So here is a slide that it has a bunch of English, not very much, but a bunch of math that basically translates your possible questions into math language, OK? So you can say, well, but why don't you consider diffusion, so molecular diffusion between particles? Then you have to take that equation that I had before and put this weird symbol there, OK? The Laplacian of f, whatever that means. And then you say, what about the real fluid, right? You don't always get to choose your steering way. Think of, again, the first example that you're looking at the river. You don't pick the velocity of the river. The river has its own velocity given by whatever natural effects. And so there is a model that describes the evolution of the velocity and the pressure of a fluid, which is a very famous model. It's called the Navier-Stokes equation. So it's this equation here, OK? And this is itself a partial differential equation whose solution is a velocity vector. But you don't get to pick it, right? Yeah, it just gives it to you in a way. So, and then you can remember that you are on a planet with gravity. And so, for example, if you're a geophysicist, you're very much interested in understanding why the ocean is a stratified fluid, in the sense that its density or its temperature varies with the vertical coordinate. So you want to take gravity into account, and you have to add another term. And then you also remember that planets rotate, and you can add rotation. And then you can remember that you have magnetic field, and then you have to add another equation, right? And so on, right? So the systems that I'm writing there, they become more and more complicated. Each one of them models, maybe a further effect. But in the end, math can just tell you something about somewhat idealized situations, OK? Which is good enough, because then, of course, besides the equation, you can think, OK, well, the ocean is within a bounded region that has weird boundaries and so on, so you have to add that as well. That's OK. Many physicists and mathematicians way before me, they thought about including all these sort of effects in some models, some equations. And what I try to do, more or less, is I'm not debating whether these models are good or not, but I'm trying to validate them in a sense, right? So if you tell me that the simple model that I showed you about, I showed you before, the transport equation, should tell you something about the mixing of two fluids, then if I prove a theorem about it, right, I really say, yes, this equation is the right equation to model this particular aspect of a process, right, steering two fluids together. And these models I studied quite a bit with a bunch of collaborators through the years. So more or less, I looked into these models over the past 10 years, let's say. Just to give you a second example of a theorem about how big of disturbances can you allow in a system to still retain stability. So this is a different problem. Again, there is a partial differential equation involved, these Navier-Stokes equations. Okay, it is whatever it is. And the setting is this one. So suppose that you're looking at a river from above, and or at a channel, right? And the observable situation is something that has maybe 0 velocities at the walls of the channel, and the peak velocity is at the center of the channel. So you can think of this as the intensity of the fluid of the water flowing in the channel. So this is a pretty stable observable situation. And how much can I perturb it? Right? That was the question. How much of a disturbance can I allow? So this, if you remember from high school, it's called the parabola. So you see it here, 1 minus y squared. This is the parabola. Okay? This is modeling this picture. And then I throw a rock in the river, right? And how big can the rock be? And it turns out that you can quantify this in some way. So the rock can be, at most, nu to the 2/3, where nu is this parameter appearing in front of the viscosity, whatever. It's 1 over the Reynolds number from the name of Osborne Reynolds, who conducted some experiments now at the end of the 19th century about this. Okay? And so we can prove quantitatively. This was proven by myself and my collaborators Tarek El-Guindi and Klaus Wiedmeyer, and then my student Augusto Lezzotto also worked on this kind of problems, is saying that, well, if you throw a rock that is at most this size, you generate a velocity field u that is not exactly the one that you observe, right? But you can tell that the one that you really observe and this disturbed one, they are exponentially close to each other again, right? And the point of all these theorems is quantifying, let's say, this exponent 2/3, the square root of nu. These are the thing I get excited about. Maybe I'm not getting you excited at the moment about. But these are really interesting and important theorems in what's called hydrodynamic stability. OK, so just a few concluding remarks. Of course, I have to acknowledge my home institution, Imperial College, for supporting me, and of course my colleagues and the administration, who I had to, let's say, interact quite a bit, especially when I, try to apply for grants. So there is always someone that tells me what to do, and that's great. So I also have to acknowledge some support from the Royal Society, the ERC, and UKRI, and the London Mathematical Society. I've had this support for quite a bit, and it's been great. And of course, so all these works that I sort of talked about, they were possible thanks to the fact that I interact quite a bit with my students, postdocs, and collaborators over the years. So that has been a really great research journey for me. And so the way I want to conclude is just to tell you a little bit what I find good about math and why I really like it. Okay. So, and I'm going to just use words from much more famous people than me. So one first quote that let's see if I can actually read it. It's from Stendhal, French writer. So I love mathematics all the more because it did not allow for hypocrisy and vagueness, my two bêtes noires. So in a sense, I've always associated math with a sense of honesty that you have to have, right? If you write a theorem and you prove it correctly, right, the theorem is just true. Right? There is no debate whether the theorem is right or wrong. The debate is mostly whether the theorem is interesting or not. That's mainly the reason why your papers will get rejected. The referee will say, "Oh yeah, the proof is correct, but it's not interesting enough for this journal." And then you're like, OK, fine. But still, I feel like lies don't last long in math. And I very much appreciate that. However, maybe the experts in the room could say that I did lie a little bit while stating theorems about mixing. And so I'm going to ask the help of Hungarian mathematician Paul Almos, who said that you're allowed to lie a little, but never to mislead. OK? So in a way, that's what I kind of did when I told you about the mixing theorems that I told you about. OK? So on the other hand, if you want to go out and say, oh, Michele Coti Zelati said such and such about mixing, you can do that and quote me. I did not mislead you at any time. I may just have said a few lies, but if I didn't want to lie, OK, the talk would have looked something like this, for 40 minutes. So this is some theorem that I proved at some point with Rishabh Gavalani, who was a student here, and Alex Blumenthal. And so this is perfectly true. It can be proven, and it's not a lie, but then I would lose everyone pretty quickly, or most of you, at least. So this is something about mixing with random flows. So I did prove a theorem about that. It's not quite looking like the one I stated. And here comes maybe another quote that I cannot really pinpoint who said it, but I found it online, which is, so how do you teach math to your students? And so the quote is, mathematics is the art of lying to your students just enough so that they can eventually understand the truth. OK? So maybe I'm not going to tell you the whole truth from day one, right? But without misleading you, I can sort of encourage you to be curious and try to really figure out the true statement of a theorem or the true solution to an exercise. This happens all the time. I mean, the coursework that I gave 2 weeks ago to my poor students in Advanced PD2 was full of imprecisions. So the statement was basically true, OK? And they did figure out that the assumptions had to be tweaked maybe a little bit to make the statement really true. But these are the sort of interactions that you really enjoy, right? You are actually discussing with your students. And this happened with my students in my class, but it happens regularly with my PhD students, postdocs, and collaborators. We lie to each other all the time, but then in the end, we figure out the true statements. And finally, I just wanted to mention this last quote by Blaise Pascal in the 1700s. So truth is so obscure in these times, and falsehood is so established that unless we love the truth, we cannot know it. OK? So I think everyone can just decide what they make of this quote, and in these times especially. But maybe I just conclude by saying that, OK, we should really love the truth, and maybe we should love math a little bit as well. Thank you very much.
Right. Thank you very much. We have about 10 minutes for questions. Who wants to go first? Over there. We have microphones that will be coming down.
Thank you. Yeah, thanks for a great talk. Enjoyed it very much. What's your viewpoint on computational theorem provers? I know that's a topical area, and yeah, at what point in your thought processes do you think they become useful?
Yes, so I think it's extremely interesting side of math that is pretty new, but in fact, I knew of this, let's say, maybe 20 years ago when I was doing my bachelor thesis. So, in fact, fluid dynamics is a really hot topic in terms of computer-assisted proofs, because people are trying to prove basically what the millennium problem for Navier-Stokes equations, so about the existence, a unique global existence of solutions to Navier-Stokes, through some computer-assisted proofs. And I've never used it myself, but I've seen now many proofs of theorems that use the help of computers. And I think, again, it boils down about being honest about it. So, of course, a proof can contain a mistake, whether it's computer-assisted or not, but you have to show the proof, right? So, of course, you have to be honest about, sharing your code, for example, or things like that. But as long as this is done, I think it's a really good direction to go. Yeah.
Another one over there.
In your proof for the mixing, you had a perturbation which was bounded above by mu to the power 2 by 3. Right? Yes. So if it's equal to that, or if it's greater than that, what kind of convergence or what kind of behavior would we get?
Yeah. So, I mean, that if it's equal, I don't know. But if it's greater than that, so there is basically your question is whether did I get the sharp estimate on the rock, right? And the answer is we don't know, because we are really able to study in this kind of setting stability problems. So if such and such happen, then things are observable, things are stable. But it's hard to construct instabilities. So you would want to say if the rock is too big, you drive away from your stable scenario. But the fact is that if you're not close to a stable scenario, you don't know what to do. So I think there are some indications that exponent 2/3 is not the sharp one. It should be smaller. But I don't think there is any proof in this sense.
Yeah, I'm not sure if lying is the right word. If you don't have the exact solution and you make assumptions, simplifications to try and reach a solution, you state that in mathematics. You don't lie about it. So I don't know why this lying is such an issue in your statements.
Yeah, because I mean, it's white lies, first of all. It's just, small lies. But I mean, what I'm saying is that I didn't lie in the sense that all the theorems that I stated, I can prove them to you, but if I state them precisely. So what I'm calling lying is more like, I didn't state the theorem as I showed in the last slide, okay? Huh?
The quotes that you made are interesting.
Yeah. I mean, no, but I thought you were referring to my statements. But yeah, I mean, I think if you state the theorems in the way that I stated them, they contain a little bit of imprecisions and lies. So a little bit of misleading is there. But yeah, I tried not to lie badly in these 40 minutes. Sorry.
Thank you. Your very first slide showed a physical model and pictures of actual behavior. How much experimentation is done to inform the development of the fluid mechanics equations?
Well, I am not doing any experiments, but some of the results that I have really do match experiments, or some difficulties that you find in proofs, you can really refer them to, you can really make a parallel with experiments, so difficulties in a way. So I have never seen an experiment myself on the things I study, but I did read papers about experiments, and so they are, pretty accurate if you can extrapolate say what they mean about what they see in the experiments and translate them into math. So now the state of the art of the experiments is really beyond my research, so I don't know, but sometimes it's pretty hard to model sort of the ideal situations that I'm looking at. So experimentalists and mathematicians, I think there is a bit of a gap into trying to talk to each other in a way. But I think some experiments are conducted here at Imperial that could be relevant, in fact, to what I study. Just I haven't had the chance to meet, let's say, the people that do them. I would love to.
Let's take a question down here.
Hi, I just want to ask you, how much of your experiment has been in a controlled setting, and do you think the results would be the same if it was not?
What do you mean by controlled setting, sorry?
By control, I mean, did you actually orchestrate what would happen at a given time?
So first of all, just full disclosure, I didn't do any experiments except maybe stirring some milk into coffee sometimes. Like that's all the experiments I really do. But I mean, this is not really a question for me in a sense that I don't know how well can you tweak an experiment to make it show whatever you want it to show, right? So this is just beyond my expertise. Is this what you meant?
No, it's just that you mentioned that there were little lies along the way, so I was wondering.
Yeah. No, but that's why I picked math and not some other subject, because I'm not very good at lying. And so maybe, no, you see, like in an experiment, it's not about lies. It's very hard to repeat an experiment 100 times to just, make sure that things are consistent, right? And the lies, it's not lies, it's just that, reality is much more complex than a math theorem in a way. And so that's, I wouldn't know. I wouldn't know exactly.
Okay, we had one more question before, someone in the middle there.
Why fluids? What got you into fluids and mixing?
Yeah. Actually, that's just by somewhat of a coincidence, in the sense that at the beginning in my master thesis, I was studying something about extensible beams. So nothing to do with fluids. When I started my PhD, I started just meeting very inspiring professors that were doing fluid dynamics. And I thought it was a good, challenging subject to get into. And I mean, then I grew to like it quite a bit, in a sense. But at the beginning, you may just think this is just an equation, like another equation that you can study. But I think I like the physics behind fluid dynamics, the math that is there, which is quite challenging, but also quite rewarding. So I think that's mostly why I got into it in the end. But I think having an inspiring person in front of you, it's the most likely scenario that will get you into study something rather than something else.
Okay, we have, I think, almost reached time now. I think it's probably a good time to stop now, and I'll call on Professor Dimitris Papageorgiou to propose the vote of thanks.
Thank you, Axel. Well, it's a great pleasure to give a vote of thanks to my colleague, Michele, who I have known for 9 years now. When Michele came, I was the head of applied mathematics, and so I was his line manager, whatever that means. So we would meet and discuss various issues and so forth. And I very quickly realized that Michele was an incredible person with a great sense of judgment. So I always looked forward to the meetings because I would get more out of them than Michele would. I would bounce off some ideas about various things going on. He was he always had amazing advice. Now, I want to say a few things about the lecture. First of all, no one has lied about anything here. I think what's going on is that there's a mathematical abstraction of physical phenomena. So you have to take the physical phenomena, abstract them into mathematical language, and then do what you can do with them. And then go back and compare with what the physical world is trying to tell you, and then you go and fix your models again and go back and forth. This is something we do. Fluid mechanics is something a lot of us do in this department. We're probably one of the few mathematics departments in the world that have so much activity in mathematical fluid mechanics. What Michele showed us is this mathematics across scales, all the way from planetary down to cups of tea. I would even go lower, actually, especially now with microelectronics, nanotechnology. It can go even further down, and things become even harder there, actually, at those scales. So Michele gave us a great exposition of all these problems, and I particularly liked slide 11 that summarized all the equations and the open problems. Cups of tea and coffee aside, I guess for me, after today, I'll never be able to have a glass of ouzo in a relaxed way without thinking of how to get to that exponential decay. So please join me in thanking Michele for this amazing inaugural lecture, and also I think we can safely inaugurate him as our first departmental mixologist.
So thank you all very much for attending. We have a public reception right outside the store.
Thank you.